Hello to this video. In this video, I'm going to show to you a first model of how to calculate what the maximum efficiency is for a solar cell of a certain band gap. And this model is the so-called Trivich-Flinn efficiency model that was published in 1955. And we are going to consider this model, first of all, to estimate how much energy can we extract from the solar cell. In previous videos, I already showed you that we have some loss mechanisms, and that is only photons with an energy larger than the band gap energy are absorbed, and the rest is not absorbed. And we saw that we have this thermalization effect, that is that the electron-hole pair loses all the energy in excess to the band gap energy Eg. So for each photon that we have absorbed, we can only extract the band gap energy Eg. And so in 1955, Trivich and Flinn suggested that this is the maximum efficiency we then can get out. We can get out a voltage corresponding to the band gap energy, and we can get out the number of electrons corresponding to the numbers of photons that were incident. That is, if we have an internal quantum efficiency of 1, each of the photons can be converted to 1 electron. And because of that, we then know how many electrons we can get out. Let's look at some summary graphics of this. Okay, so let's look at an example here. So let's consider we have a band gap energy of 2 electron volts. This means, as shown here, that all photons that have an energy of more than 2 electron volts are absorbed. And also we just saw that only the band gap energy, Eg, can be extracted for each photon. So that means if we have a photon of 2 electron volts, we can extract the full 2 electron volts out of this photon. So at the energy of 2 electron volts, if we have an incident spectral irradiance of 1.4 watts per meter squared per nanometer, it means we can also use this full energy of this full power of 1.4 watt per meter squared per nanometer. If we now, on the other hand, consider we have an energy of the photon of 3 electron volts, and that would correspond here to maybe 1.2 watts per meter squared per nanometer as incident power, then we cannot use all of the energy. But of the 3 electron volts, 1 electron volt is lost to thermalization and only 2 electron volts can be extracted. That is 1/3 of the incident power is thermalized, is converted to thermal energy, and only 2/3 of the power are available for electricity generation. Therefore, inherently, due to the thermalization of the 1.2 watt per meter squared per nanometer, we can only use something like 0.8 watts per meter squared per nanometer. And this situation, if you have some other photon energy, is of course more and more energy is thermalized, the higher we have the photon energy. For example, for a photon of 4 electron volts, half of the energy will be lost to the thermalization process, and only half of the energy can be used for electricity generation. We can also look at this plot in terms of the wavelength that is shown here. So again, the 2 electron volts correspond to 620 nanometers about down here. So in wavelength, the shorter wavelength photons have a higher energy, so the shorter wavelength photons are absorbed, while the longer wavelength photons all are not absorbed. They are passing through the solar cell. So only the blue shaded region of photons is absorbed, And again, we cannot extract all of the energy, that is this difference seen here, because each photon can only contribute an energy of 2 electron volt to electricity. All the rest is lost to thermal energy. If you're looking at this graph, then you might think, well, this is not so good because lots of photons are not used at all. So let's make the band gap smaller. 2 electron volts is maybe not a good idea. So let's look at an example of 1 electron volt. So here you can see the case of 1 electron volt. So for 1 electron volt, all photons that have an energy more than 1 electron volt are absorbed. But for each photon that is absorbed, we can also only extract now 1 electron volt. That means at a photon of 1 electron volt, we can use 100% of the energy. At a photon of 2 electron volts, that was about 1.4 watt per meter squared per nanometer as the spectral irradiance, we can only extract half of that, or we can only use half of that for electricity generation, because 1 electron volt is thermalized right away. So only at 2 electron volts, only half of the energy or the power integrated then over time can be used. And therefore, we now see from this graphic here that we absorb now more photons, but also we lose a lot more energy to thermalization. And therefore, if we would go to even smaller band gaps, this effect would become more and more drastic. That we can, if we choose a band gap of 0.5 electron volts, we can absorb even more photons, nearly all the photons, but we can use very little or extract very little of the energy because so much of the energy is lost to thermalization. And this is therefore, there must be some optimum band gap. If the band gap is too small, all the energy is lost to thermalization. If the band gap is too large, no photons are absorbed. So therefore, there must be somewhere an optimum of the band gap, and actually the optimum is somewhere around 1 electron volt to 1.5 electron volt. That is the kind of optimal range where you get the most energy extracted out of the solar cell. So if you also look at this now in terms of wavelength for the 1 electron volt, so 1 electron volt corresponds to 1.24 micron here, and therefore we have all the photons absorbed that have a wavelength smaller than 1.24 microns. And this is actually all of the visible wavelength range. The visible wavelength range extends from something like 400 nanometers to 700 nanometers. So for this band gap of 1 electron volt, all of the photons in the visible wavelength range are absorbed. And so a good solar cell should actually look black. It should absorb everything in the visible spectrum. And that we can see by the black color. So if the solar cell does not look black, it means part of the photons is passing through in the visible spectrum and not being absorbed. Of course, our eyes cannot take notice how much of the infrared or ultraviolet radiation is absorbed by the solar cell. So for this band gap energy of 1 electron volt, therefore the photons shown in blue here contribute an energy that is shown by the blue area. And now if you want to calculate the solar cell efficiency, it means we start with this power conversion efficiency here. So we have to look at what is the external power that we can obtain divided by the incident power. I showed you in a previous video that we can also calculate the photon flux, that is the incident photon flux, phi incident, by integrating over the photon flux per wavelength array interval. And the absorbed photon flux is in this model that all of the wavelengths are absorbed up to the band gap wavelength, means that the absorbed photons are the integral of 0 to lambda band gap integrated over the interval, over the spectrum. So over all wavelengths, we need to integrate from 0 to the band gap wavelength. I will go back once more. So we integrate from 0 to the band gap wavelength, or the wavelength corresponding to the band gap. This gives us all of these photons. So the phi absorbed in this simplified model is all photons are absorbed that have a wavelength shorter than the band gap wavelength. And once we know how many photons we have, we can then, of course, calculate from this what the absorbed power also is, because the absorbed power we obtain by just converting the number of photons to the absorbed power, and that is done by integrating the spectral irradiance from 0 to lambda g to the bandgap wavelength and multiplying with the area A. So this part of the photons here is absorbed in the simplified image. And the simple model now, the Trivich-Flinn model that was published in 1955, says, okay, you can, all of the photons that are absorbed need to be multiplied with a bandgap energy Eg. That gives the power that we have, that we can extract from the solar cell, and the efficiency following the Trivich and Flinn model is then this external power divided by the incoming power. And if you formulate this in terms of the spectral irradiance, you get this equation here, in which you do a weighing of the spectral irradiance with Eg over E photon in order to take into account this thermalization effect here. And I actually calculated now what this model efficiency here would be. So we obtain for a bandgap energy of 1 electron volt, considering this air mass 1.5 global reference spectrum, we obtain an efficiency of 48% following the Trivich and Flinn model. So this is a first model to give you a feeling of what power or what energy can be extracted from a solar cell. You have to consider at least the which photons can even be absorbed by the semiconductor material, and you have to consider the thermalization effects, and the two combined then give you the Trivich and Flinn efficiency, eta TF. Thanks for watching.